You can see my presentation and hear me?
Yes, yes, you can. I can see and hear you.
So welcome everybody to our fifth and last ENTRAIN trainer session that will be about basics and extension of the QM system. Today it is a pleasure for me to welcome our external guests from Germany. They are students from the bachelor course Renewable Energy in Rottenburg. Thank you for joining us today. My name is Heidrun Kögler. I work for the Energy Agency of Styria and will lead you through the program of today. Together with the AEE INTEC, we are organizing the trainer sessions within the ENTRAIN project. Harald Schrammel and Ramerstorfer from the AEE INTEC, who are presenting most of the inputs of today, are leading the QM Heizwerke program in Styria and are experts in the field of renewable district heating systems. As usual, in the beginning, just a few words concerning the technical details. This session will be recorded and also might be released afterwards. During the event, please mute your microphones and switch off your camera for saving bandwidth. And if any questions come up during a presentation, please note them and ask them in the discussion rounds after the presentations or in the end of the training session. You can also write your question in the chat window during the presentation, and we will come back to it after the presentation. Here's just a short introduction to the ENTRAIN project for our external participants. The overall aim of the ENTRAIN project is to reduce the local carbon footprint by intensifying the use of renewable energy, and as a result also to reduce CO2 emissions and improve the local air quality in the target regions, which are Italy, Germany, Croatia, Slovenia and Poland. One of the solutions for that at local scale is to install district heating networks powered by local renewable energy sources, which are biomass, solar, waste heat, heat pumps, or geothermal energy. Forging ahead these solutions in the target regions, this is the main focus of the ENTRAIN project. So far, only a handful of Central European regions have introduced effective policies promoting renewable district heating, and most of them don't have a lot of experience with renewable district heating systems from a technical and economic perspective by now. In Austria and Germany, in both regions, we have advanced planning capacities and long-term experience in the field of renewable district heating systems. And to share this knowledge is the aim of the trainer sessions, like today. One special thing in Austria is the QM Heizwerke, which is a quality management process that is also a precondition for financial incentives for renewable district heating systems in Austria. And one part of the ENTRAIN project was also to adapt and translate the guidelines and planning handbooks of the QM Heizwerke for all target regions. And this is what our today's training will be about, the basics and the extension of the QM Heizwerke system. So, including the extra training of today, in all 5 trainer sessions will have been held from the beginning of the project. And for a short overview about the inputs of our previous trainer sessions, I again want to recall very shortly what we already learned. Our first the trainer session in November 2019 was about how to develop a project from the scratch. So it was about the first steps for planning and initiating renewable district heating systems. The second training in June 2020 was about fundings, economics, and financing of renewable district heating systems. There we learned some details about economic profitability calculations, how to compare heating costs of individual heating systems and district heating systems. We also heard about some examples of economic feasibility from Germany, and also about the contracting model as a possible financing and operation model. This training was also supplemented by one presentation at the online web meeting in September 2020, which was about how to convince potential investors of district heating systems. After that, the third Train the Trainer session, which was held in December 2020, it was about emissions, air quality, and fuel and ash logistic. This is very important for each operator of a combustion plant because burning biomass produces many different kinds of emissions that have to be reduced as good as possible. And how you can do that and which legal framework in the different countries regulates that were content of the third training session. As an add-on of the web meeting in April, we invited Christian Holter, who took us to a virtual study tour to the solar thermal and biomass district heating plant in Mürzzuschlag. And our fourth Train the Trainer session was it was the last training session that was held in June 2021. It was about operation and optimization of renewable district heating systems. In this training, we took a closer look at the technical aspects of optimization and modernization of district heating systems, as well as on practical examples and optimization measures. Also, operation and plant monitoring according to the QM system were topics of the last training. And here is the agenda and the contents for today's training. After my introduction, Christian Ramerstorfer and Harald Schrammel from the AEE INTEC will talk about. They will talk first about the basics and then about the details of the QM system in two presentations. After the first two presentations, we will make a short feedback round if there are any questions. Then at 10:20, we will have a 15-minute coffee break. And after that, we will continue with the topic integration of alternative renewable heat sources and the extension of the QM system. The inputs of this presentation were developed also as one part of the ENTRAIN project within the last months. And this presentation will again be held by Harald and Christian. At 11:20, we are looking forward to welcome our external speaker, Harald Plaschek from the company Steps Ahead. He will talk about absorption heat pumps for biomass district heating and about waste heat utilization. And finally, after a further discussion and feedback round, we will come to an end at 12:15. So let's start with our first presentations, the basics and details of the QM system. Christian Ramerstorfer and Harald Schrammel will give an overview about the basic idea of the QM system, the basics of the QM guidelines and the QM planning handbook. Then they will go more into detail and explain the documents and checklists of the QM system, and also talk about important milestones and design guidelines within the program. Christian and Harald, it's your turn. You can start now.
Christian,
Chiara, could you please give the moderation role to Christian?
Christian, yes, of course.
Yes, please.
Okay. Now you are the moderator, please. start. Thank you.
You see the presentation in full
Yes.
screen? Yes. All right. So very warm welcome also from my side for today's last Train the Trainer session. Yeah, I will start with QM system basics, some basic thoughts about what is QM Heizwerke and why we are doing or applying this quality management system, and some examples of achievements that could be done by applying this quality management for biomass district heating plants. And the second half of the presentation, I will hand over to my colleague Harald Schrammel, who will then continue with some basics about the QM process and also about document tools, project types, and maybe also a little bit about what QM is not. But first, yeah, let's start with what is QM Heizwerke. So it is a quality management program for biomass district heating plants. The name QM Heizwerke is only in Austria. Main objectives to improve the quality and efficiency of biomass district heating plants and the networks, to have a professional planning and execution of these plants, yeah, reliable operation with low maintenance efforts, low emissions in all operating conditions, and a sustainable long-term operation also. This program is founded by or part of the Klimaaktiv series of programs in Austria by the Ministry for Climate Action and Environment and so on. And the basic idea is to have funding only given to high quality plants. So it's in Heidrun already said it. It's a prerequisite to do this QM system to get fundings for biomass district heating plants in Austria, which is very good situation. Yeah, also the optimization of existing plants is one important point, and know-how transfer, as we do it here, is one of the points from the program management. What you can see here is the international logo we also did during the ENTRAIN project now, so QM biomass DH plants, and the link to the official homepage that's online since this year. Next, yeah. So where does this come from? Initially, it was made in Switzerland. So this whole QM system was invented in 1998. Since 2005, the development is also supported by Austria, Germany, and yeah, we are very glad, and it's a really highlight of the ENTRAIN project also that we have a new member from Italy now. So since end of last year, Ape Friuli Venezia Giulia is an official member of the working group for biomass district quality management for biomass district heating plants. Yeah, you can see here a photo from our last working group meeting also that was done in Italy with the new members from there. So why should we do this quality management? First of all, biomass district heating plants are long-term infrastructure projects with high investment, and the planning significantly influences the project success. So it's very important to have a good quality from the beginning during the conception of a plant, and in the end to avoid stranded investments. Then also during operation to have a consequent monitoring and optimization. And as we had also in Austria a lot of troubles in the past, to not make the same mistakes again and again. So this all can be done with the help of QM also, because if you have a look on where the costs are determined in the project, so this is at the very beginning. As you can see here, about 70% of the costs that will occur in a biomass district heating project are set in the beginning and during the concept and planning phase. During detail engineering, about 20%, and only 10% then at the procurement. So it is very important to have a good look on the quality already at the very beginning, because it's also very difficult often to correct planning mistakes afterwards, and sometimes even impossible. So for instance, if a district heating network is built too widespread because some assumed in the beginning were wrong, then this cannot be corrected again afterwards. And also correcting planning mistakes is very expensive afterwards. So it's important to be safe from the beginning, let's say. Some general claims are that biomass district heating must become better and cheaper. So because it's also in some competition to other heating systems, and so the main goal is low heat generation costs. To apply systems that improves quality continuously, so during the whole plant life also. As I said, professional conception, planning and implementation is important. And financial support should only be given to high quality systems, which is also, of course, important for the ministry or for the state where the money goes to. So some quality objectives that let's say form the basis for the QM system is to achieve a reliable low maintenance operation. This is also important for heat supply safety and in terms of costs, of course. High utilization ratios and low heat distribution losses. You will see some examples afterwards about that also. Low emissions, as also Heidrun also already mentioned, is important in all operating conditions. To have precise and stable control systems, and all in all, ecological and economic sustainability. So, and this for the whole lifetime. And QM helps at defining and checking criteria for the quality of the planning of a project, but also for the operation afterwards. Here there are some additional objectives or also services that can be done by QM. So there's it is also a chance that there's an independent consultation to the plant operators, for examples, apart from the planners or also the component deliverers. So it might be important to have such an independent position during discussion of issues. And what is also important to have know-how transfer also within the community, let's say, so learning from mistakes of others, and QM and the Q managers which guide or are responsible for the implementation of the QM system in the project and guide a project, are also open for new and proven solutions. So they are innovators. Yeah, and one of the additional objectives of QM is also, of course, that it does not cost too much additional work and budget. So to have an impression about, yeah, maximum up to 1% of the investment costs of a plant is spent on QM. So this is not really a big amount of budget, but can save a lot of costs and yeah, gain great effort for a biomass district heating plant. So some of the achievements that already could be gained in by the application of the QM system in Austria is that we have a standardized quality requirements, especially in Austria, where there's also a database operated where the whole process is done with it, and where the plants have to yeah, submit data to it. We have a very good collection of data in between of a lot of plants. So it is also compulsory to do monitoring and optimization. Yeah, we have a lot more, so don't want to mention everything here. What is also very important thing is that documentation is improved. Just as an example here, regarding the reduction of heat distribution losses. So you see in the first two columns plants that are not guided with the QM system, and then in the third and fourth column plants with QM support, and you can clearly see that the share of plants that have heat losses of more than 30% decrease significantly. So the red share is decreasing with QM. So of course this is a very good achievement in terms of energy efficiency and also sustainability. Then other example, also regarding common mistakes that have been made and should be avoided through the application of the QM system, is that there's often or has been often insufficient knowledge of basic data during planning. So especially heat demand and heat capacity planning, or data from the heat consumers is an issue, which in the end often leads to lower heat sales than expected, and this can of course be critical for economic viability of a project. So you see here some exemplary heat generation costs and also the heat sales that can be gained by the plants. And yeah, for some cases economic feasibility is really close. Of course, this is also just a spot of 1 year, so this changes of course regarding heat sale from season to season, but yeah, it's important to have that in mind. And Another example for common mistakes is regarding the temperature difference between supply and return flow in the district heating network. This has a high influence on the operation costs because the lower this temperature difference is, the more water volume has to be transported through the heating network, and pumping costs increase. So and what you can see here is that the share with good temperature differences of above 30 Kelvin yeah, is much lower than with temperature differences below 30. So this is an evaluation we did from data from this database I mentioned before. And of course, it would be good for the plants or an objective to be as high as possible. So but of course not too easy to achieve. So yeah, this is also something that can be improved steadily through operation and during the life of a plant. So some more common mistakes, only 2 or 3 important points I would like to mention here. First, oversized boilers and oversized network pipes is often a problem. Then too extended and widespread district heating networks is one big issue. So often there are consumers connected to a district heating network that are too far away from a heating plant or the existing network, so that they can be supplied economic efficiently. So yeah, some more you can read afterwards. So yeah. So at this point, I would like to hand over then to Harald.
Okay.
I don't know. Do we really?
Chiara, can you make me the presenter, please?
Yes, of course.
Okay.
Okay. You are the moderator now.
Oh yeah. Automatic.
Oh, sorry.
Do we have to stop first, or is this? No.
No, I think it's fine.
It's okay.
Okay.
Just give me a second. All right. You should see it in a minute.
Yes.
We can see it.
All right. Thank you very much, Christian, for the introduction. I take over and show you something more about the QM process. The QM process is a process to avoid these common mistakes, which we just heard of. So let's dive a bit deeper into the QM process. Before we do that, Heidrun, please help me to keep the time schedule and shout out loud if I'm far too long. Thank you very much.
You have now 15 minutes until the end of the first presentation.
Yes, thank you very much. Okay. What is the basic principle of the QM process? We want to have a suitable planning process because, as Christian said, planning is the most important thing of every project. It costs money in the very beginning. It costs a lot of money. You should not save on planning costs because you will regret it later on. So we need a high quality planning to get high quality plans. One very important part of the QM process is that we have clear roles in the whole process, from plant owner, who is the planner, who is the queue manager, who is the representative of the plant owner if they don't do it themselves, and which responsibilities do each of these persons have. This is clearly defined in the QM process. This is one major part of the QM process. Another major part is we have a clear project structure in milestones, and within each of these milestones, there are requirement of data and documents. This is clearly defined. Which data you have to provide at which stage of the project, which documents you have to provide at which stage of the project. This is very important to avoid a lot of mistakes, to have a high quality planning. And the third basic principle is that in the very beginning of a project, we want to define the quality which we want to reach in the end of the project. This means defining the quality at the beginning of the project. We see later on how we do that. But it's very important that you know in the beginning what you want to have in the end of the project. This is paving the way to get the plant you want. The QM process is shown here. I hope you can see my cursor. Maybe I change it to, no, sorry. You saw the basic process before. Here, this is another way of showing it. We have 5 milestones, starting from a very early project phase, preliminary study, until the monitoring optimization. This means the plant is in operation already. And during each of these milestones, we have a quality loop. This means we have an independent quality manager. This quality manager is checking the status of each milestones. Do we have the documents we expect? Do we have the information we need to close these milestones? This data is evaluated and checked by the quality manager. And in case there are any issues, the quality manager reports to the planner and the plant owner, and together they try to correct these shortcomings. Okay. I think it's important to show you something about the timeline of a project. You learned a little bit of the QM process already. We will dive deeper into it later on in the next presentation, what each milestone means in detail. But you see here the basic overview. You start a project in the very early phase with a preliminary study to check out if it is feasible to start even planning such a project. Even there, you should start considering QM guidelines so that you have a basic idea of what QM expects of a good project. We learned in other trainings that it is very important because you immediately find out if a project is feasible or not if you start considering some basic benchmarks of QM. So starting from the first project idea, keep QM in mind. As soon as you have a decision to keep on continuing the project, so go into a more detailed planning, into a design planning, you should implement QM, starting with milestone 1. And then doing the full process over the complete planning phase until the commissioning and operating phase. Do not forget, that's a very common mistake within the QM process, do not forget to finish the process. There are very important steps in the end. We showed it in the last training. This is monitoring and optimization, which is sometimes not considered as important anymore. We have the plant now, it's running, that's fine. But in the last training, we showed you why this is extremely important and you should never stop doing monitoring and optimization. Okay. What you see here is in an early phase of the project, you start contracting heat consumers. Even though it is not clear yet if you will be able to build the plant. Contracting of heat consumer will never end. I will show you later that this is a very important criteria to decide if we continue building a plant and at which stage we are able to close milestone 2, for example. The whole QM process is defined in the Q guidelines. These guidelines are available in English. and thanks to ENTRAIN project in many other languages as well. There you can find everything about the QM process. An additional very important document of the QM publication series is the planning handbook. The planning handbook is upcoming in English and other languages as well. We are not fully ready yet, but we are working intensely on it. There you have a lot of support for the whole planning process, a lot of basic knowledge, detailed technical knowledge. This is in accordance to QM, but the QM process, the roles, the tasks and responsibilities, everything is defined in the Q guidelines. So everything else are additional supporting documents. The standard hydraulic schemes, I will talk about that in the next presentation. We see right next on. This is an integral and important part of the QM process. And then we have additional supporting documents, for example, if you want to for the procurement of wood boilers, for example. The structure of the Q guidelines image the QM process more or less. We have the definition of the participants of the project. I mentioned that already. In the very beginning, we have to establish the QM process. So there, we do not have know-how transfer to all participants so that it is clear for all participants what's their tasks and duties. And you might get some recommendations from funding agencies as well. Then we have the structure with the milestones in chapter C. The services the plant owner has to deliver, and E, very important, the services and requirements the main planner has to deliver. Christian mentioned QM sometimes tend to cause a lot of work, but we say that's not true because a comprehensive planning include all this data, all these documents. So there is not much of additional work to do for the QM process. It's just to collect all the documents and data you need within a serious and comprehensive planning procedure. Okay, this is done for milestones 2 to 5. And this part is just a special fuel definitions. We have some add-ons within the Q guidelines, which are very important, especially the annex part here. We see some tables of these annex parts later on, and we see examples of the checklists, which are a very helpful tool for doing the QM process. I mentioned the upcoming planning handbook. You see a first translation of the content. So Christian has translated the whole book already. We have to do some final fine-tuning before we can publish it and start translating it into Italian and other languages. But here you see, this is really a comprehensive collection of knowledge, of data, of examples, which really can help you to plan a nice and efficient biomass district heating plant. It's a support for planner, queue managers, and operators. What we want to mention here is as well that we have different types of projects we guide with QM. QM basically was invented for building a new plant, for doing the whole planning process. But in Austria and other countries, we have a lot of existing plants doing plant enlargements. So QM can be applied for plant enlargements as well. The same applies for optimization, modernization, revamping, refurbishment, however you want to call it. Of course, for existing plants, you have to be more flexible because you cannot fulfill all QM requirements, for example. And we have some special plant configurations. I will talk about that in our last presentation. This is just to show you, I don't go into detail here. There's a difference between optimization and revamping. This is a guideline how you can handle that, how you can see that. This differs a little bit. It depends on the funding organization, on the funding process sometimes, how you see that, but usually refurbishment, revamping is a complete modernization of the plant, while optimization is something continuously ongoing, and this is just more or less minor adjustments of the plant. I mentioned it already, QM, the QM process seemed to be quite strict. It is strict. It's very complicated. It's clearly structured. But if you read the Q guidelines, you will see that you have to dive really into it to understand all of these things. But at the same time, there is flexibility. QM does not want to forbid any solutions if you can prove why you choose a technical solution, why you choose this dimensioning of the plant, why you choose this setup of the plant. So QM is not about forbidding, QM is about proving. So if you can prove that you have a better technical solution than QM has, you're very welcome. So QM is open to develop, to include new concepts, but the very important thing is we do not like experiments. So we do not want to make the same mistakes again and again. This is why there is flexibility, but you have to prove it. And at some points we are very strict and say there is no flexibility at all regarding the heat sale. Christian mentioned it. This has a very strong impact to the whole process, for the dimensioning, for the economy of the project. So there is not much of flexibility here. You have to secure your heat sale before you start the project.
Harald, 3
yes.
minutes.
All right. Thank you very much. The standard hydraulic schemes, I think we skipped that. We have a lot of common mistakes here. We can talk about it later. Another thing which allows not too much of flexibility is the fuel quality. It's very important that the fuel quality fit to the furnace technology. Otherwise, you run into the first problems if you start up your plant. This is very clear. We see this later on. This is closely related to dimensioning of boilers, of the whole plant, of choosing the setup, and this has to fit together. The Q requirements for the fuel storage are very flexible from my point of view. There is a strict definition, but it really depends on the fuel logistic concept. There are different concepts, direct ones, indirect ones, mixed ones. So you should keep a close look. The idea is not to have too large fuel storages, too large investment costs for various reasons, but it depends on the logistic concept. For existing plants, we mentioned that the QM guidance is possible for existing plants as well. You, of course, have to gain allow more flexibility because we cannot change everything with existing plants. And this is important as well. We see in Austria, we have very, very highly skilled operators and planners operating 50, 60, 100 plants. So for them, you can allow more flexibility because you can trust them at some point. They know what they do. They have their own interest in having very efficient and good plants. So then you can step back a little bit with QM and say, that's fine what you do. I think this is my last slide anyway. Yeah, so I'm good in time. Just to mention what QM is not covering. QM is focusing on the planning process, on technical issues and the first operating period. It's not directly addressing other parts you need as well during operating a plant, like all administrative issues, how you organize plant operation, how you organize insurances, billing, customer relations, and all this. Maintenance, operation logbook, customer relations, I mentioned it. So this is not covered within the QM process. But I want to mention it that there are a lot of optimization potentials as well within these non-technical issues. So to consider that as well from an early stage on, try to learn from good examples with that. So thank you very much. We are finished for this part of our presentation. I think we skipped the question phase, Heidrun, and we jumped into the next presentation. Is this right?
Yes.
All right. Okay, then we collect questions for the break or before the break. All right. So then I hand over to Christian as well. Chiara, please.
Okay. Okay. Just one moment, please. Okay. 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 Christian, you can go.
Yes. So here I am again. You see the presentation again?
Yes, you can see.
Yes.
Okay, thank you. So I will go on with some more details about the QM system. Yeah, first a little closer look, as Harald already said, about documents from the QM system, and a bit closer look on the process with the milestones. Harald again will then continue with the second half of the presentation about efficient and low emission plant operation, and yeah, demand assessment, appropriate system selection, dimensioning up to standard hydraulic schemes. So very important topics of the QM system, and a bit of the relations between these topics maybe also. So what can be found in the documents from the QM system? So most important document, as Harald already said, are the Q guidelines. There you can also find the different templates for the Qplan main document and the Qplan, which is summing up basic data and indicators, key figures that let's say define the quality criteria, and to make it measurable if you achieve the quality you want to achieve or not. And this Qplan is updated in every milestone, so it also makes it possible to compare it throughout the whole process, and see if everything is on the right path, let's say, or if there's a problem coming up anywhere. Then there's the Qplan NX, also a very important document. We will have a closer look on that afterwards also, which is where all the work of the Q manager in the end is documented during the process. Checklists for the milestones, and also other documents, as Harald already mentioned. So like this standard hydraulic schemes that are related to the hydraulic and control solution, where there's also can also be found templates in the Q guidelines to fill out, to not miss any point that is important, and so on. So let's have a closer look on this Qplan. Here you can see what is recorded in the Qplan. So all the main key technical indicators, for instance, heat demand of all the consumers, district heating, grid losses, and so on. So the most important technical data of a plant, but also economic data like investment costs, for the central heating plant and the district heating grid. So out of these figures, there can also be calculated and some key performance indicators you can see here. So key figures like the linear heat density, a very important number for example, and like specific investment costs. So that's the most important points about the Qplan. And then the Qplan NX, a different document where there's a template in the Q guidelines which documents what the Q manager is doing. So and also how the QM is implemented. So you see here a form to check which, for instance, which documents have been submitted at every milestone. Then yeah, some examination of the previous project process, how the quality was inspected, and here the last page of the Qplan NX, there's also documented which documents were handed in, what is the further time schedule, and a very important field for the Q manager, yeah, a final assessment by the Q manager. So he should state there, he or she, of course, should state there, what should is everything going in the right direction? Are there some different measures, or should be measures be taken to ensure the quality of a plant? And yeah, but it's important that the Q manager is always only making recommendations to a plant owner, so he's not able to decide that a measure is then really implemented. He is recommending, and this Qplan NX is also then the proof, let's say, of the work of the Q manager and of how the plant owner decided. So the plant owner still can say, no, I don't want to do that, and then the Q manager can say, okay, but I recommended it, and you see if yes or no in this column here. Yeah, and this has to also be signed then in the end by the plant owner, the main planner, and the Q manager. So all the three of the most important participants of a QM process, and yeah, so that they agree how to proceed with QM, let's say, in the project. So let's have a bit closer look on the process itself with the 5 milestones. Harald already mentioned some of the points. So in milestone 1, this is where it is documented how the QM process, or that the QM process is implemented. There's also the contract with the quality manager done, so a plant owner or an authorized representative of the plant owner is naming a person to be a Q manager for the project, and they do a kick-off meeting then with the main planner also in order to establish the QM process. And yeah, do a first Q plan with the key figures I just showed before, which is then also updated in every milestone. Then yeah, milestone 2 is reached when when the detailed planning phase is completed. So very important data here is our consumer lists, documenting the heat demand, and yeah, of a project. Also, of course, the whole technical data regarding plant components, the layouts, technical description, heat loss calculations. So all the technical data of a plant is documented in milestone 2 before it is even built. So also economic data is very important. So first economic profitability calculation. Yeah, and again Qplan here, and also this Qplan NX I just showed. So the report of the Q manager, where he says is he is the quality okay from his point of view regarding the all the detailed planning. Milestone 3 is then reached after the tendering, so before the start of the actual construction of the plant, and he's also, or the queue manager should then also visit the plant and do a report about the proceeding of the plant direction, and should also document if there are changes done to the initial plan that was there, so taking photos and so on. Yeah, so that's the first part of the process from milestone 1 to 3. Just as an example here, what is in this checklist that were mentioned before in the Q guidelines for just exemplary now for milestone 2. Yeah, you see here that what is done in the Qplan NX again. So most of the points here mentioned already, I think. Yeah, and this checklist is used by the main planner also to compile the necessary documents and deliver them to the queue manager. Yeah, and that's the most important thing here, I think. So here, really a screenshot from the document in there. For instance, for the checklist milestone 2, you can find again all these quality criteria. So, for instance, for the list of heat consumers that has to be delivered for milestone 2, there is then written that at least 70% of the heat demand should be secured when reaching milestone 2. So do not build a plant before you know that at least 70% of the heat you planned with can then actually be sold. That's yeah, such quality criteria is also can be found here then within these checklists. Here's some more for milestone 2. So regarding demand assessment, appropriate and appropriate system selection. Yeah, there are a lot of these points to be checked for milestone 2, and then rest of the QM process, milestone 4, 5, and the very important completion. So in milestone 4, the plant was built, and so that the actual operation of the plant starts. Here it should be documented what were the final investment costs, a final list of the heat consumers of all the plant components, of course. So documentation of the plant is a very important point. Then also queue manager has to do a site visit again to show, lay a certificate that the plant components are really in operation and installed. As this is also important for the funding agency to be sure that the money is going into into the right components that were mentioned or applied for funding. Then there's a commissioning log, and then what is very important, an optimization concept. So because milestone 5, or the last milestone of the QM system, is then reached after a first operating period of 1 year. So and the objective of this milestone 5 is then to see, okay, now we have a first year of operation, let's see what can be optimized a first annual operating report has to be done in Austria, and then also beyond the QM process for another 10 years. So this is also a very important source for plants data. Yeah, and plant monitoring on the evaluation of operation is a very important and integral part of the QM system, which is then documented and in Milestone 5. So yeah, that's, I think, the most important about the QM process in detail here. So now again, I would like to switch to Harald.
Okay, one moment. Okay. Okay, Harald, you can start. It's up to you now.
Harald, 35 minutes.
All right, thank you very much. Yes. Christian was very fast, so I have time to talk. Yes, I think this should work now.
Yes.
All right. Before we start with system selection, standard hydraulic solutions and all this, I have to admit that it is very, very difficult to bring you into a QM process in that short of time. So Christian and I tried to give you an overview to point out some important things, but as our Italian colleagues know, we had a 4-day very intensive training to get closer to this QM system, and still you need a lot of experience. You have to do it. You have to work as a queue manager that you can really dive into that. So it's really a challenge today. I hope it's not too boring for you, that you see a lot of these things. I think many of these things would need more explanation, but we do what we can. If you're interested, we have more information. You have to start studying the Q guidelines, for example, the planning handbook, and I'm sure then there will be a lot of questions arising. So if you want to go into more detail of the QM, start studying these documents and start getting in contact with us. All right. We had one training where we were talking about low emissions. So this is one key element what we want to reach. Christian mentioned we have the combustion of biomass causes emissions. Biomass is renewable. It grows in our woods, but we still have to use it very efficiently, because we need biomass for other applications as well, not only for heating. So we have to use it efficiently. We have to use it with low emissions. What does this mean? How does this is related to system selection, to the mentioning of these plants? That's what I want to show you here. What is an efficient low emission plant operation? I have pointed out a few things here. The most important thing is, it's hidden between in here. I'm changing to laser pointer. The furnace has to be operated within designed and guaranteed conditions. That's very important. If you're outside of these operating conditions, we will have bad combustion conditions. This causes a lot of emissions. This causes a lot of other problems within the whole plant. We want to have high utilization of the biomass boilers. This is an economic criteria, actually. We want to have high full load operating hours. Biomass boilers are expensive. They are large, they cost a lot of money, so we want to utilize these investments. Of course, we have to correspond to the load demand. We want our boilers to follow the set point specifications, and which is implemented here already. We want to operate within design criteria. This means we do not want to have start and stop operation. We do not want to have standby operation. This always causes a lot of emissions. This causes slow efficiency and reduce the lifetime of the plant. In all load ranges, this is very important, not only during official emission measurements from our authorities. No, in all load ranges, we want to have low flue gas temperatures and low emissions and high efficiency, meaning low excess air ratio, for example. So this is the main idea, what we want to achieve. How can we achieve that? Experienced planners, we mentioned it. No experiments. If you're not so experienced, trust existing and proven solutions. And do not come up with new solutions. I'm pretty sure that 30 years ago people already tried it and maybe failed. So take care here, or take an experienced consultant into the team, whatever. Use existing know-how. This is the same thing, which I already mentioned. Very, very, very high focus on the demand assessment. The demand assessment decides a lot of things within the whole planning process. This is deciding how large our boilers will be, what plant setup we choose, and it decides the economy of this plant. So high effort is needed for this demand assessment to know how much heat we will sail at what time. So we need the load profiles and the amount. And always consider investment costs versus operating costs. No short-term thinking in long-term projects. This is a long-term infrastructure projects which will last the next 30 to 50 years, especially the district heating network. So always consider investment costs, short-term versus operating costs, long-term. So cost saving, yes, but in the right way, on the right place. There are primary and secondary measures to reduce emissions. I don't go into detail here. Primary measures are related to the combustion conditions itself, and secondary measures are filters, precipitators, and other measures to reduce emissions. Both is standard state-of-the-art technology and has to be applied anyway to keep emissions as low as possible. But these measures do not work if you have an inappropriate system configuration. That's very clear. If we are operating our equipment outside the guaranteed conditions, what I mentioned before, then they cannot work. So example, start-stop operation. Or very bad, a lot of bad load operation or low load operation. Flue gas cleaning systems might turn off. You might get black fumes, as you see here. We don't want to have that. This is causing a lot of problems, especially with the people in the area, your customers. They might wonder, this doesn't look renewable, to be honest. So we need a proper plant. And of course, it's not only the emissions, it's low efficiency, it's high maintenance effort, reduced lifetime of plant components. So you cause a lot of issues if these things are not designed correctly and operated correctly, of course. Okay, so how do we select a system setup, a system configuration? How do we dimension this plant? We have a heat demand assessment. We had one training, but you have to go. You can go much more into detail here, which we are not able to do today. So if you work on that, try to be very precise to define your heat demand. Based on this heat demand, you select a system. This means how many production units do I have? Is it only biomass? Is it a monovalent plant, or is it a bivalent plant? Do we include oil or gas peak load boilers, or do we include CHP plants, waste heat, whatever? We see in the next presentation then, makes it even more complex, of course. So here we have to decide the basic system setup based on our heat demand. This is all based on our heat demand. How we do that, we see on the next slides. So we select the systems setup together with the dimensioning of the production units. This is closely related to each other. So this is our heat demand curve, annual heat load curve, and this is a very complex example I show you later on. I just want to show you here. Here we decide, is it one boiler or is it 2 or 4 boilers? Which fuels are they, and how large are these boilers? And this is again related to the hydraulic scheme, to the hydraulics concept, how we connect these boilers to each other. And of course, very often forgotten, it's not only a hydraulic scheme, it's not only dimensioning the plant, we have to operate this plant. This means we need a control strategy for the whole thing. So what I want to say here is, it's not only a hydraulic scheme, it's an overall concept. Our standard hydraulic solutions are closely related to system configurations, to dimensioning, to benchmarks for these systems, and the control strategy. This is all integrated in a standard hydraulics solution. We often see the mistake within the QM process that they choose a hydraulic scheme. They say, serial, parallel, 2 boilers with storage, without storage. And then they think, oh, it's the piping, it's maybe some measurement points, and that's it. This will not work without a tailor-made control strategy fitting to your plant setup and your hydraulic scheme. So it's an overall concept, including all these aspects. Within QM, we offer an Excel tool. This Excel tool is pretty often mentioned in the Q guidelines. It has a very, very bad name, a long name. We call it Excel tool for demand assessment and appropriate system selection, something like this. So it's, yeah, not the best name, but we did not find another one. However, we cannot go into detail with this Excel tool now. This will take another day, I guess, to go through it. For you, important to know is that this Excel tool includes many of the basic design criteria based on which standard solution, which system setup you use. What we see here is a bivalent system with 1 biomass boiler and an oil boiler, and the base load production unit, for example, a waste heat source or something like this, or maybe it's a CHP. It doesn't matter at the moment. So for you, important to know is there is an Excel tool. It's capable of producing a lot of important information. It's capable of doing a plausibility check of your heat demand assessment as well. And what you see here is more or less one of the final outputs. So we see our annual load duration curve, simplified of course. And here we define the size of our biomass boiler, the size of our oil boiler. What we get out of here is already the heat production of these units. And you have a very good starting point to go into the detailed engineering. But here you define the setup. You don't, of course, you don't have to use this Excel tool. You can do it however you want. You should consider the things I will show you in a minute. So we have to ensure that we operate our biomass boiler, especially the biomass boiler, within all load ranges in the defined operating conditions. So that the biomass boiler is not going into start and stop operation, that this biomass boiler is not going into below the minimum allowed load rate of this boiler. Of course, maybe I have to mention this, or I jump onto the next slide. Here, this is a very important table. You find it in the Q guidelines in the annex, so in the part at the end where you have all this important information compressed. This defines what QM says about load rate of biomass boilers. Of course, manufacturers often say my boiler can be operated at every load condition. That's true, but you will not be able to keep emission limits if you, for example, operate a large boiler below 30% of load rate, depending on the water content. Of course, you have certain load rates, part load rates, which you should not go below. This is a table show you an indication. Of course, sometimes there are new technologies, special conditions which may allow you to go lower, but really take care here. This low load operation of biomass, especially of large biomass boilers, cause a lot of problems. This is the main part. This is part of the complete system, the holistic system to define a setup. Is it a one boiler plant? Is it a two boiler plant with or without storage? This lies behind of all this. I do not want to show this example in detail. There is one important thing you should keep in mind. We are talking about minimum average daily heat load. Minimum average of 1 day. This is very important because we expect that you have a system with a storage. Systems without storage, you should totally forget in the beginning. We do not recommend such systems anymore. Of course, you can build plants without storages, but this is only applied in very special conditions. So for standard conditions, a biomass district heating system without a storage is not state of the art anymore. So you should consider a storage. Very important, you should consider a storage with a control strategy. Your storage will not help you much at all if you do not include it in a load management and control strategy. Okay, as soon as we have a storage, this storage is responsible for load management, harmonization of a daily load. This is why we are do this dimensioning with a minimum daily average load, because the rest of the is doing the storage. And we want to have stable operating conditions for the biomass boiler. We do not want to have immediate load changes. We do not want to have the biomass boiler operated below these values here. How you can use these values here is shown in the example down here. Okay. Then we jump into other tables, which you can find in the Q guidelines as well. What you see here is for each setup, for each plant configuration. For example, this is a bivalent plant with one biomass boiler and one oil or gas boiler. Of course, we always consider the oil and gas boiler just as a peak load boiler and a backup boiler. The main, our idea is that the main heat production is done by the biomass boilers, of course. We have names for it. This is WE4. Sorry, this is coming from German. This is a two boiler plant biomass with storage, and this is another setup. For each of these setups, you get a set of design criteria. We say, for example, with this setup, the annual heat production with biomass should be 80 to 90% at least. Of course, we have in Austria, we often see that these rates are much higher because people are motivated and they want to produce as much as possible with biomass. But you really have to take care here. If you want to increase these values, your boiler size will significantly increase. This means you get problems within the part load operation phase. So this is all about these dimensioning tables here. So we get a clear benchmarks, what we want to have for the utilization of the investment, the full load operating hours. We expect that they are quite high. And of course, we say low load operation has to be in compliance with table 16, which is this table here. Okay. So, and of course, there's an influence if we have automatic ignition or not, the fuel quality, and there are guiding values about enlargement reserves. So, of course, a district heating system is always growing, enlarging, and many people consider quite large reserves, so they buy larger boilers. But in many cases, we see that 10 years later, these capacities are still not used and they still have problems in part load operation. So take care here with these reserves. You have to be very sure. Again, I have to refer to the heat demand assessment where you should define all this, even enlargement and enlargement path for that. And the storage capacity is defined here as well. Here we got the feedback from Italy. This was very interesting. We got the feedback that planners say, "Oh my God, this causes huge storage tanks. This is not possible. We never built large storage tanks like this." This is closely related to the temperature difference in your district heating system or in your production system. So take care about return temperatures. Of course, if you have very high return temperatures and low temperature differences, you need large storage tanks to fulfill this criteria, but that's not the intention. So take care of the temperatures as well. Okay, so now I jump into a more complex, even more complex topic. This is the hydraulic schemes. We're talking about, something like this. This is integral part of this dimensioning process of choosing the setup, and I try to provide some fundamentals for this process. As I said, and I want to highlight it again here, this is not only a hydraulic scheme. It's not only about the piping. It's not only how we connect these boilers. It's an integral process. We have a hydraulic scheme for each boiler plant setup, but this is connected to a control strategy. This is connected to a measurement standard, at which point we do measure what, to a monitoring concept. So it's an integral concept. Okay, so I jump back, sorry. The idea is that we provide one proven hydraulic circuit per system configuration. It's not fully true, to be honest. We have parallel circuits. We have serial circuits solutions as well. I do not go into detail here. These are special solutions, but the standard solutions are a parallel setup of our boilers. Very important, the heat generation system and the hydraulic system should be able to be extended. I mentioned already, systems are growing. We might need another boiler in future. So the system should be designed in a way, the control strategy, that it is possible to jump from one boiler setup into another one without changing everything. This means leading boiler and following boiler are not hydraulically defined. So both boilers in a two boiler setup can be the leading boiler and the following boiler. You can operate the system with one boiler, with both boilers, so you have full flexibility. Of course, only with parallel circuits. We define the main control variable with storages, and for now I'm just talking about systems with storages. This is the charging status of the storage. This is not very common. in let's say standard heating systems. Usually you take the main flow temperature. This has to be provided, then everything is fine. But we want to operate our boiler steadily, no immediate load changes. This means we need a storage tank. I mentioned that already. But this is only working if the storage tank is doing load management. This means the main control variable to set the boiler load is the charging status of the storage tank. This is why we need 5 measurement points in the storage, for example. This is why we need a control strategy for the boiler. This is defined in the standard hydraulic solutions. We will not be able to go into detail here and discuss these concepts. We have different ways to define the set point of the firing rate, which should be included. Strict decoupling of hydraulic circuits with low pressure difference, very important as well. We do not want to have influences between our hydraulic circuits. We said we need maximum flexibility, that these boilers can be operated independently, and we do not want to have load changes of one boiler influencing the other boiler then in the hydraulic circuits. It's very important. And of course, we want to design all consumers with the lowest possible return temperatures. That's a tricky point. But let's say here we start at the district heating plant itself, so that we design our district heating system and the feeding point in a way that we have the chance to maintain this. And of course, then we have to do optimization at the consumer side, because in the end the consumers define which return temperatures we will have. We want to have minimum differential pressure for each connection. We do not want to waste electric energy for pumping. And in order to allow a nice and smooth control of our hydraulic systems, we need certain valve authority. So the dimensioning of the control valves of each of the hydraulic circuits is very important as well. We will not be able to go into detail here as well. Okay. To be considered that we have to meet the requirements of the boiler manufacturers, of course. So they define certain flow rates over the boiler. They need a certain water quality, min-max temperatures, things like that. This is high priority within each control strategy concept, of course. I mentioned that we do not recommend systems without storages for obvious reasons. There are special applications, one or another I will show later on, where we can do that, but not for a standard system setup. Load and storage management are common weak points, closely related to who is responsible for defining a control strategy, who is responsible for programming, realizing it, who is responsible for checking it afterwards in the monitoring, who is responsible for the data acquisition so that we are even able to do monitoring and check what our plant is doing. These are very important points. You should define that in the very beginning. QM is asking for that. So within QM, it is very clear. The standard hydraulic solutions include a control strategy. Sometimes it's sometimes it's ignored and people don't do it. They hope that the boiler manufacturer knows what he's doing, and they provide a control strategy. That's very dangerous. So as a planner, you should work on the control strategy together with all manufacturers, and then you need a good way to realize these projects, these control strategies. Okay, this is yes. Okay, I think I'm already at the end, more or less. I showed you this. This is just an example. Again, do not misunderstand a standard hydraulics solution. Don't think the simple way and connect it as you see here. It's an integral concept containing a lot of information, a lot of knowledge to have these boilers, the whole concept working together and reach finally the results we want to have. High efficiency, low emissions, high durability of our plant components. You have a very good basis. Of course, as we mentioned, QM has some flexibility. You are, of course, allowed to choose different setups, different solutions, but you should, what QM says is, then please describe it the same way as QM does. And prove it the same way as QM does, that this is working. Okay. At the end, just a disclaimer, because people mention this every now and then, that our hydraulic schemes do not include safety equipment, and this is very dangerous. It is very clear that you have to meet all national regulations regarding safety equipment, thermal safety discharge device, safety valves, whatever. We do not include that into our hydraulic schemes because it's not the same in every country, not the same in every region. Of course, you have to meet all national standards and regulations for that. So thank you very much. I hope I could give you, together with Christian, we could give you a bit of an overview, a bit of an insight, even though I said it's very, very difficult to understand this all in that short of time. So we are happy to answer your questions. Thank you very much.
Thanks a lot. It was very interesting, very comprehensive. There's one question from Johanna in the chat. Harald, can you answer it, or? Johanna writes, she has a...
I'm reading it.
Yeah, okay.
Okay, Johanna, I think that's a very good question for our next presentation right after the break, because there we will talk about future concepts, or I have to say modern existing and future concepts of renewable district heating, including biomass and many other heat sources. Then, of course, we will have to be more open-minded, more flexible regarding dimensioning of these boilers. But I will talk about that in the next presentation. I hope that's fine for you.
Yeah. Are there any other questions? Harald Schrammel has another question. He writes, if we talk about 100% renewable heat, we do not want to use additional oil boilers. What would be your solution?
Maybe I've chosen a bad example, Harald. There are, of course, solutions without oil and gas boilers. Using oil and gas boilers for peak load and backup is an, let's say, common solution, and it's starting to change. We have a lot of projects in Austria where we have just two biomass boiler setups without oil and gas boilers. They are working nicely. Sometimes they're at even a smaller boiler. Maybe it's even a 3-boiler plant. They have this, let's call it summer boiler, which could be, let's say, a small boiler from mass production. It could be even a pellet boiler. So there are nice setups nice solutions which you can use. We have them in our standard hydraulics solutions as well. Then it is possible to cover 100% with renewable heat. Other options could be to use biogas or biogas instead of natural gas for your gas boilers. We had some plants, some experience using vegetable oil instead of fossil heating oil. But this is sometimes a bit tricky. So I heard about some experience where people were not so happy because you have to take care a little bit with vegetable oil. If you do not use this boiler frequently, you have to take care about the storage of vegetable oil because it gets solid at lower temperatures. So then it's not usable anymore. So you have to take care where you put your storage tanks. So there are some issues with the vegetable oil. But as I said, very nice standard solutions are 2 or 3 biomass boiler setups without natural gas. What you have to consider is a backup solution, because we want to guarantee high supply security for our heat customers. And sometimes they say an oil or gas boiler is very high security to provide heat at any time in case we have any issue with one of the biomass boilers. As we know, biomass boilers are larger, have a lot of conveyors and fuel transport equipment as well. So there could be an issue, but if you plan it properly and operate it properly, it should not. However, if you have a setup without oil and gas boilers, what people do is that they include emergency connection points so that they can use mobile heating devices in case of an emergency. I suggest to consider that anyway, even if you have an oil or gas boiler, in case of a large breakdown, a large emergency, which we had to face in Austria as well, one or another time, it's very important to have such connection points outside of the heating plant so that you connect a mobile device. And as an operator, you should be aware of where you can order or where you can get such a device and what time you need to get such a device.